Hello, class. Due to popular demand from your teacher, Mr. Briscoe, I've decided to make a second video, and this time on HPLC or high performance slash pressure liquid chromatography. So let's have a look at the study design dot point for this topic. It says the principles of chromatography, including the use of high performance liquid chromatography, HPLC, and construction and use of a calibration curve to determine the concentrations of an organic compound in a solution. So basically, HPLC is a type of chromatography technique which pumps the mobile phase through a tightly packed stationary phase under high pressure to determine the concentrations of and the identity of compounds in a mixture. We'll define the terms mobile phase and stationary phase later, so don't worry. But let's look at some of the principles of chromatography. So generally, chromatography is a technique used to determine the concentration of substances in a mixture based on their varying absorption, which is a bit more specific to HPLC. And it can also be used to identify compounds based on their unique retention times determined by their adsorption to the stationary phase. So now on to the process of HPLC. For this example, I'm just going to use reverse phase chromatography, or RPC for short, but the general theory of this type of process can be applied to any type of chromatography. So for this, the stationary phase, which is the solid onto which the components of the sample adsorb onto, is set up using silica gel, which are small particles that are nonpolar with a high surface area to improve the separation of the compounds in the mixture. So that's going to be their stationary phase. But their mobile phase, which is the phase that flows through the stationary phase carrying the components of a sample within it, is typically something a bit more polar, such as water and methanol. So after we set up the column, the polar sample is then injected into the column and pumped through to the stationary phase. It is here that certain compounds in the sample would adsorb greater or form a more extensive interaction with the stationary phase, if you like. So if you think back to the like dissolves like rule, compounds with a similar polarity is likely to dissolve better in one another, which in this case would result in more adsorption onto the stationary phase, whereas compounds with more differing polarities is likely to repel one another, hence leading to more desorption. Therefore, it is important to know that you only really want to perform chromatography when there is a contrasting polarity between the eluent and the stationary phase in order to achieve the best results. This is because, what we're mainly trying to do with chromatography, or the main focus of it, is to identify the presence of compounds in a mixture by their difference in polarity or the interaction with the stationary phase, which thereby generates a range of different retention times specific to each and individual molecule. So, for example, if we had a non-polar substance in the sample, we'd probably expect it to have relatively a higher retention time. And likewise, if we had a polar substance in the sample, then we'd expect that to have a relatively lower retention time. So what happens next is that the eluent passes through the stationary phase and into a detector through a beam of UV light. Well, the UV light is there because organic compounds are typically pretty good on their absorption of UV light. And the differing ability of compounds in absorbing light can therefore result in varying quantities of light received by the detector. And this, alongside with the differing wavelength of light it can receive, the detector converts all of this information into an absorbance measurement. The process is obviously repeated with all the detectable substances in the mixture, and the resulting trace is called a chromatogram, like the one you see here. So for example, in this one, each individual peak would represent a separate substance that's been detected by the detector. But ultimately, don't worry too much about the actual process. You just need to understand that a detector converts the information of a HPLC trial, such as absorbance, concentration, and retention time of substances, into a chromatogram for a mixture at a specific condition. So next, the retention time of the substances in the compound is collected and compared with the retention times of the standard solutions of the same substance ran under the same conditions used to identify or verify the identity of the compounds. It is crucial here that you know that they must be ran under the same conditions, as, for example, if you change certain conditions such as temperature or length of the column, then their retention time is likely to be altered. But don't worry about that too much because we're going to discuss this shortly. But after comparing the retention times, you might want to find out the concentration of a particular substance. And you can do that by plotting a set of concentrations matching with their peak area from the standard solution of a specific substance, just like how this table has done here. And this information from this table can be plotted onto a graph to produce a line of best fit that we call the calibration curve. And then we can use this calibration curve generated from our standard solution to predict the concentration of a particular substance in the mixture, since from the chromatogram we would already be able to calculate the peak area. So you can think of it sort of as using the y value to predict the x value like this. So now for the final bit of the lesson, we're just going to finish off by talking about some of the factors that affect the analysis of HPLC. So starting off with an obvious one, if the polarity of the stationary phase and the mobile phase is different between trials, then you're probably going to expect different results. I've already discussed this one before, so I'm not going to waste too much more time on this. But for the length of the column, the retention time is expected to increase as the length of the column increases because there is simply more distance for the element to travel. And for pressure, obviously, when you apply a greater amount of pressure to something, in this case the element, you would expect it to flow through the column a bit quicker, which leads to a lower retention time. Now, this is something I haven't really talked about, but is the surface area of the stationary phase. But if you have small particles that make up a big surface area, it's going to be a bit harder for the liquid to pass through because there's not so many gaps between the particles for the liquid to exploit and pass through. Hence, that would result a higher retention time. But if you have bigger particles, for example, those typically leave behind bigger gaps between them, which means liquid is easier to pass through and hence leading to a lower retention time. And for temperature, you should know that at higher temperatures, the substances typically pass through at a quicker pace as there is a quicker exchange between the compound and the stationary phase, which results in a lower retention time. And obviously, if the compound was smaller in size, you'd expect it to generally have a lower viscosity and flow through the column more easily, hence resulting in a lower retention time. So that's basically all the factors that you're going to see that affects HPLC. But one crucial thing that you might want to know is that the concentration does not affect HPLC, since the analysis of the compound is primarily based around their difference in polarity. And obviously, you would know that is independent of concentration. Oh, and one final thing, you should know that HPLC is both a quantitative and qualitative analytical technique, and that the qualitative aspects comes from the identification of the compounds based on their retention time, and the quantitative aspect is obtaining the concentration of each compound based on the calibration curve. Well, I think that's all for this lesson. I hope you enjoy the lesson, and please do not hesitate to throw any questions to Mr. Briscoe, but please do hesitate asking me anything about this because I'm well and truly washed by now. But nevertheless, I hope you found this somewhat useful, and I'll see you in my next class.